Alright, now we want to look at how to use dimension analysis to check if a particular equation is valid or correct. That's what we want to look at now. Now, the first question we're going to look at is if the work done by an ideal gas, if the work done by an ideal gas is given by the equation or relation W is equals to PV. If the work done by an ideal gas is given by the equation W is equal to PV, where W is work, P is pressure, then V is volume. W is work, P is pressure, V is volume. Check if this equation is correct. Check if this equation is what? Is correct. Now, if you want to do this, look at how you do it. Before you can apply this application of dimensional analysis. Now, before you can apply something, you should know it. So, before you can apply dimension analysis, you should know how to calculate dimensions of physical quantities. And we have already done that video, and it's here, dimension analysis. It's inside the channel. You can go and look at that. If you don't know how to calculate dimension of physical quantities, the video is there. Just look at it. Then, if you know how to calculate dimension of physical quantities, yes, you are good to go to application. Go and apply them. Start applying them now. Now, let's therefore apply to test this equation now. Look at what you do. The first thing, identify each terms present. Look at this place now. We have three terms, W, P, and V. They said W is work, P is pressure, V is volume. Now, next, write out their dimension. What is the dimension for work? Work is M L square T raised to power minus 2. That is work. Equal to, what by pressure? What is the dimension for pressure? M L raised to power minus 1 T raised to power minus 2. Times, what about volume? What is the dimension for volume? L raised to power minus 3. That is the dimension for volume. Then the next thing, you will solve out the mathematics in the right hand side, because the left hand side will be free in most cases for this particular application of dimension analysis to check whether a particular equation is correct. So next thing, this remains. So this will be equal to, let's solve this out. M is just single. Then we have L raised to power minus 1 times L raised to power 3. What will be the answer? You pick one of these two bases. For me, this is, they are the same. Pick one of the bases, then you add up the power, which is minus 1 plus 3. Okay, let me remove this stuff. Let me remove this stuff. Let me remove that thing. So that will be equal to M first, then you pick one of these two bases, L, then add up the power minus 1 plus 3. Then T is just 1. T is power minus 2. So if you want to finish this up, this is what we have in the left hand side. That will be M L square 3 raised to power minus 2 is equals to M minus 1 plus 3, that is 2, L square, then 3 raised to power minus 2. We check this and this, they are the same. If they are the same thing, look at the M is M, L square, T raised to power minus 2, T raised to power minus 2. So both sides are the same thing. So if they are the same thing, it means the equation is what? Is valid. But if they are not the same, it means it's invalid or not correct. So this equation now is very correct. So let's look at another question. Now let's look at this question. This number 2. Now, example 2. Example 2. Let's look at this. A student, that is a particular student. A student defined the quantity power as the product of force and velocity given by the relation P is equals to FV. So the student is telling us that power is equals to force times velocity. That's what the student is saying. Check if this definition is correct. Check if this what you are having here is correct actually. But because power, we know, is work done over time. That is the definition of power, the rate at which work is done. But one student is actually telling us that power is still force times velocity. Can we say this student is correct? Not yet. We are going to test it if it is valid. Test for the validity of this equation. How are you going to test it? Using dimensional analysis. How will you do that? Already said it. Just like example 1. Identify this term. P is power, F is force, V is velocity. They say power is equal to force and velocity. Product of force and what? Velocity. So what is the dimension for power? What is the dimension for power? Power is M L raised to power minus, like raised to power 2, T raised to power not minus 2, just 2. Then T raised to power minus 3. This is the dimension for power. What is the dimension for force? MLT raised to power minus 2. What is the dimension for velocity? LT raised to power minus 1. Remember, anything standing alone is having a power that is equal to 1. So this L here is having a power that is 1. If you see anything just standing without any power, it's having an imaginary power that is equal to 1. Latent power. The next, we can now say M L square 3 raised to power minus 3 is equals to M. Now, L raised to power 1 times L raised to power. We just say L times L. L times L will give us L square. That's already true with that. L times L, L square. Then T raised to power minus 2 times T raised to power minus 1. Just pick one of the base because we have T, we have T. They add up the power minus 2 plus minus 1. Remember that minus times minus is equals to plus. Minus times plus is equals to minus. Minus times, that is plus times minus, is equals to minus. Plus times plus is equals to plus. So if the two signs are not the same, the answer will be minus. If the two signs are the same thing, the answer will be plus. So minus times plus, that is plus times minus, will be minus. So that we'll be having M L square 3 raised to power minus 3. Then M L square 3 raised to power minus 2. Minus that is plus times minus give us minus 1. So that will be equal to M L square 3 raised to power minus 2 minus 1 will give us minus 3. So let's check. We have M, we have M, we have L square, we have L square, we have 3 raised to power minus 3, we have 3 raised to power 3. Valid. It is valid because this equation here and this equation in the right hand side, both of them are the same. If they are the same, it is valid. If they are not the same, it is invalid. Take note of that. Now let's look at another question. All right, now let's look at this question as question 3. If the velocity of sound in any medium, is given by the relation V is equals to the square root of E over rho, or you can also give it this way, E over rho raised to power half. Either I give it this way or this way. If the velocity of sound is in any medium It's given by the relation v is equals to square root of e over rho, or e over rho raised power half. Anything raised power half means the square root of that thing. That's the meaning. Where v is velocity, this v is velocity. E is Young's modulus. E is Young's modulus. And rho, this means rho. This means rho. It's like this. It means rho. Is density. V is velocity. Velocity. E is Young's modulus. Then rho, this rho in the downside. This one in the downside is rho. It's called density. Check if this equation is correct. Check if this equation is what? Is correct. So how do we check if this particular equation is valid? The first thing, you identify all the terms present. We have velocity, Young's modulus, density. The next thing, write out their dimensions. What is the dimension for velocity? Lt raised power minus 1 equal to the square root of what dimension for Young's modulus. Now, take note, Young's modulus has the same dimension with pressure and stress. Take note of that. Pressure, stress, Young's modulus, shear modulus, they all have the same dimension. Take note of that. So, what is the dimension for stress? The same dimension for pressure, which is m L raised power minus 1 T raised power minus 2. Then over, what about density? Density is mass over volume. So the dimension for density is the dimension for mass over the dimension for volume, which is mass over the dimension for volume is S cube. If you now move this up, the power will change sign. We have m, calculator m, L raised power minus 3. That's the dimension for density. So that is very simple to do. We already done some those steps. We have m, L raised power minus 3. So m will cancel m. Then we'll now be having the square root of. Now remember, we have t raised power minus 1 in this place. So if this, okay, L raised power minus 1 in this place, we also have L raised power minus 3. So this power of this L will go and mean this other L here. And the power will change sign. That is mathematics for you. Power will change sign. If any power crosses this division line, it will change sign. So we're going to have L. We want to move everything in this denominator to the numerator. M, I've already cancelled M. That is gone. So we don't move this L. No, we just move the power. Since we already have L here, there's no need of moving this L. Don't move the power to go and make the power of this L in that place. So we're going to have L raised power minus 1. So this minus 3, if we cross this division line, it will change sign to plus 3. Then t raised power minus 2. So that will give us of L t raised power minus 1. It's now equal to the square root of minus 1 plus 3. That is 2. L square. Then t raised power minus 2. So you need to remember, I told you square root means raised power half. So I just going to change it to that. Anything square root of anything means that t raised power half. We have L square t raised power minus 2 every t raised power 1 over 2. So what I'm going to do, this power here will affect this and this. Look at what I'm trying to say. It's something like this will be like this. If you just this power to put this bracket will be L square. Then raised power. L square raised power means you will multiply the two powers. Multiply this power and this one. 1 over 2. Then t raised power minus 2 times, say 1 over 2. Just like that. So 1 over these two will cancel these two. These two will cancel these two. This one will be left with my, okay, because I'm saying these two will cancel this and this. Only one will be left here. Then one will also be there. So we'll now be having L t raised power minus 1 will be equal to, so this one is left with just L raised power 1, which is same thing as L. Then t raised power, we have minus here, minus 1. That's minus 1. Because if you have t raised power minus 2 times 1 over 2, we cancel this, we'll be left with -1. Or you just use calculator, do -2 times 1/2, it will be -1. Then 2 times 1/2, it will be 1. So let's check this and this. Are they the same? L 3 square minus 1, very correct. This one is also valid. So that's how you do it. You just have to know how to solve mathematics in the right hand side. That is the major thing there. If you know how to do that, you're already good to go. Now let's look at this other question. Let's look at this next one. Now the time taken for a body to displace from one region to another, or from one position to another, is given by t is equals to the square root of 2d over a. T is equal to the square root of 2d over a, where t is time, d is displacement, and a is acceleration. T is what? T is time, d is displacement, a is acceleration. Check if the definition or equation is correct. Remember I told you, first thing, identify what is present. We have time, displacement, acceleration. Next, you write out the dimension. What is the dimension for time? T. Then equal to, we have 2. What is the dimension for displacement? The dimension for displacement is the same thing as the dimension of distance, and the same thing the dimension for length. Displacement, distance, length, radius, diameter, perimeter, they are all having a dimension that is equals to L. So the dimension for displacement is L, then over. What is the dimension for acceleration? Acceleration is LT raised to power -2. That's the dimension for acceleration. LT raised to power -2. So L will cancel L. They will now be having the square root of 2 will be left to the upper side over t raised to power -2. So since there's no t in this upper side, we are going to move everything upward. Then this power will change sign. Remember that. Assuming there was t upward, we just move only the power to go and make the power of the t in the upper side numerator. So we're going to have the square root of 2. If everything here moves up, we have t, but this power will change to from -2, now change to what? +2. So we can also write this on this way. T will be equal to, we have root 2 times the square root of t raised to power 2. So this will cancel the square root. Square can cancel square root because it's something like this. Square root of t square, which is equal to, remember I told you square root means something raised to power half. Will now be raised to power what? Raised to power half. These two will cancel these two. That's why square can cancel square root. So we are now going to have the square root of 2 times t. Now let's check if the equation is correct. If the equation is valid, we have t here, we have t here. But we'll have half here. Do we have half here? No. Now, is it valid or not? It is valid. Sir, why is it valid? Because there's 2 here, but there's no 2 in this place. There's no root 2 in this place. Why are you telling us it's valid? It is valid because constants does not affect dimension. Constant number do not affect what? Dimension. Take note of that. In dimension analysis, 4t is same thing as t, because all these constant number will not affect. The only thing that do affect in dimension analysis are physical quantities, not constants like 1, 2, 3. Any number do not affect. Coefficients, like all those coefficients that are numbers, do not affect dimension. So that's why we are just going to forget about this and pick only the quantities present. The quantity here is t raised to power 1. The quantity here is t raised to power 1. So since we have both quantities in the two sides, just forget about this root 2. Assume it does not exist because numbers does not affect dimension. Please take note of that. It's very, very important. The package is also valid. It's also valid. Please take note too, because numbers will not affect dimension. We have t here, we have t here. There's no other thing in this place other than t, which is just this number. So number will not affect. Assuming we're having a here now, it is not valid because a is a physical quantity which acceleration or something else. Assuming we're having like a velocity or volume attached to this, it will not be valid. So take note of that. It's very, very important. So let's look at another question. All right, now let's look at this question. Look at this question. The distance moved by body, is given by the equation d is equals to a over t square. The distance moved by a body is given by the equation d is equals to a over what? A over t square. Where this distance, a is acceleration, and t is time. Check if this equation is correct or valid. If we say distance equals to a over t square, is it correct to say something like that? That is the question now. So let's go. First thing, identify the terms present. We have distance, acceleration, velocity. Next, let's just insert their respective dimension. For distance, dimension is the same thing as L, which is for length. For acceleration, we have LT raised to power minus 2. For time, we have T raised to power 2. So the next thing, we have to apply rules of indices. A raised to power m divided by a raised to power n will be a raised to power n minus m. Another thing is just to, since we already have t here, don't move this power up and it will change sign. It's still the same thing. So we're going to have LT raised to power minus 2. If this 2 moves up, it will change from plus to minus because 2 is the same thing as plus 2. Any number that don't have sign is positive. Take note. So if it moves up now, it will change to negative 2. So that we'll be having L is equals to LT raised to power minus 4. We have A, we have 3 raised to power minus 4, but there's no 3 raised to power 5 there. So since both sides are not the same, the thing is invalid. So if you quote this formula, you are not correct. The formula is very, very incorrect. It's invalid. So this particular one now is invalid. So this has to know whether it's invalid or not, because both sides are not the same. Let's look at another one. All right, the work done by a body. The work done by a body is given by the formula W is equals to M D over T. The work done by a body is given by the formula MD over T. What is M? What is D? What is T? Where W is work, M is momentum, not mass. M is what? Momentum. D is distance. T is time. T is what? T is time. Check if this equation is correct or valid. Check if this particular equation is valid. So let's see if this equation is valid. What is the equation for work? Work is M S squared 3 raised to power minus 2. Equation for momentum. Momentum is mass times velocity, which is M LT raised to power minus 1. So momentum is M LT raised to power minus 1. What is the dimension for distance? L. Dimension for time is T. So we're going to have M L squared 3 raised to power minus 2 is equals to, we have M S times L, that will give us L squared. That will give us L squared. Then this is 3 raised to power 1. Anything that don't have power is having power that is equal to 1. If this one moves up, we change to minus, from plus to minus. We are going to have t raised to power minus 1, minus 1 again. So this will give us m s square t raised to power minus 1 will give us what? Minus 2. ms squared 3 raised to power minus 2. So check this side. This side is ms squared 3 raised to power minus 2. This side is also what? ms squared 3 raised to power minus 2. So that shows that this equation is valid. Is what? Is valid. From your mere look, it may look invalid. But from analysis, it is what? It is very, very correct and valid. So this is how we rule here. This is how we rule it. Okay, let me look at one more. Now let's look at this. If the power developed by a body is defined by a relation P is equals to A over T squared. If the power developed by a body is given by the relation P is equals to A over T squared, where P is power, A is acceleration, T is time. Check if the equation is valid. Check if the equation is what? Is valid. Power has a dimension of ml square 3 raised to power minus 3. Acceleration has a dimension of m. Okay, there's no m self. lt raised to power minus 2. Then t has a dimension of time, has a dimension of t, that is squared. So I'll give us lt raised to power minus 2. If this 2 cross to this side, it will change from plus to minus. We have minus 2 again. We're going to have m. We're going to have ml squared 3 raised to power minus 2 is equals to lt raised to power minus 4. Minus 1, minus 2, minus 2 give us what? It will give us minus 4. So if you check what you have here and what you have here are not the same. It shows this one is invalid. It is very bad. So this equation is bad. It's not correct dimensionally. So you cannot define power this way. So this is how we rule. You just, the first thing, identify the terms present. Next, write out their dimensions. Then next, solve out the right hand side. Then check if both sides will be the same. If they are the same, it's valid. If they are not the same, invalid. Thank you. I love you all. Please remember to subscribe to this channel. Please also share and like this video. You are blessed.